Wonderful. Okay, hello everyone. My name is Steffen Lindner. I'm a postdoctoral researcher at the University of Tübingen. And today I'd like to talk about P4TG, which is a 1 terabit per second traffic generator for Ethernet IP networks. This is joint work with my colleagues Marco Herberle and Michael Ment. I'd like to start my talk with a short motivation. Why did we develop P4TG? Then I'm going to give an overview of P4TG. What protocols does it support? What statistics does it measure? And what is the general architecture? Afterwards, I'm going to talk a bit about the implementation concept on the P4 side. And then I'm going to show some evaluations, especially what is the accuracy of P4TG and what are sample use cases where we, or where others already have used P4TG. Then I'm going to show a small demo, and finally, I'm going to conclude my talk. Okay, what is the motivation for this talk and for P4TG? When we develop new protocols or new network equipment, we need to test them with realistic traffic rates. And nowadays, realistic traffic rates are 100 gigabit per second or even more. And typically, traffic generators are used for that purpose. But when we look into the literature, the top 10 most used traffic generators are all software-based. There are tools like iPerf2, iPerf3, NetPerf, MoonGen, T-Rex, and many, many more. However, when you once tried to generate 100 gigabit per second with software, or even more than 100 gigabit per second, you may have found it quite difficult and that you need large amounts of compute resources for that. So in the best case, we need some kind of hardware acceleration. And the bad thing is that these commercial hardware-based traffic generators are very expensive, tens of thousands of dollars or even hundreds of thousands. And this is not feasible for example, research institutes, small universities, or even mid-sized companies. And when you want to do multi-port testing, so several 100 gigabit per second for business-grade switches or routers, then that's not feasible with software-based traffic generation, at least not in a cheap way. And that's why we had the idea for P4TG. P4TG is a traffic generator and analyzer written in P4 with the Intel Tofino ASIC. The Intel Tofino ASIC, at least in Germany and as a university, costs around 8,000 euros, which is quite cheap compared to commercial hardware-based traffic generators. And the great thing about it is that it already offers built-in capabilities for traffic generation. And that's why we had the idea we could implement measuring functions in P4, as well as a nice configuration user interface so that we can easily configure the internal traffic generation. And with this approach, we are able to generate constant bitrate traffic, as well as post-sort traffic. Post-sort traffic is traffic with random inter-arrival time, so the time between two packets. As I already said, we use the internal traffic generator or the internal capabilities of the Intel Tofino for packet generation. And then we apply a packet header rewrite for traffic randomization. So for example, we rewrite the Ethernet headers, we can randomize the IP header, change the VLAN tag, and so on. P4TG supports various encapsulation protocols like VLAN, QNQ, MPLS, or VXLAN, and P4TG is able to generate up to 10 times 100 gigabit per second traffic on 10 ports, so in total 1 terabit per second. We not only generate traffic, but also measure traffic and analyze it. And we do that directly in the data plane with P4 for the highest precision. For example, we measure the layer 1 and layer 2 send and receive rates. We also measure these rates individually on a per stream basis. We can define several streams with P4TG, and then we can monitor each stream independently. We also measure the send and receive frame sizes and types, like unicast, multicast, VXLAN, and so on. And when we generate traffic and feed it through other network equipment, get the traffic back, then we can also detect packet loss or packet reordering. So we can test whether other network equipment, the so-called device under test, has enough performance for our use cases, or whether there's too many lost packets. We also measure the send and receive inter-arrival times. This can be useful when other equipment changes the shape of our traffic. For example, when another device introduces bursts in our traffic, then we would see that by the difference between the deviation on the send side on the interarrival times and on the receive side. And finally, we also sample round trip times so that we get an idea what is the processing time on our line. So we tag a packet with a timestamp, send it out, and when we get it back, we know how long the processing took or how long our path is. The general workflow with P4TG is as follows. We have a user interface that is written in TypeScript and React, where a user can configure the traffic generation in its browser. The user interface then interacts with a controller via HTTP calls, and our controller is written in Rust and exposes a REST API to configure the traffic generator and uses then afterwards the BF runtime gRPC interface of the Intel Tofino for configuration. And of course, you don't need to use the user interface in your browser. You can simply use the REST API, for example, for test automation. We also built an automatic test bench for network equipment where we use the REST API of P4TG for automated testing. Okay, now we have a rough idea what is P4TG and what are its capabilities. Now I want to talk a bit about the implementation concept. And we can split the implementation concept into 3 parts, into the traffic generation, which is split between control plane and data plane. Then we can generate traffic. In the next step, we need to collect statistics. This is only done in the data plane so that we can get very precise measurements. And in the last step, we need to retrieve the statistics to visualize them in our user interface. And this is again split between the control plane and the data plane. Let's talk first about the traffic generation. I already said that we use the internal traffic generation capabilities. And to that end, the controller configures the Intel Tofino to generate up to 7 different packet types with a given target rate and a given frame size. A packet that we define consists of an Ethernet header, an optional VXLAN header, an optional encapsulation like VLAN or MPLS or QNQ. Then we have a regular IP header, a regular UDP header, and our custom P4TG header that we use for packet loss detection, for example. And finally, we have the payload, which is randomized, and the size of the payload depends on the frame size. When we have configured the Intel Tofino, the Tofino will generate these packets with the given target rate, and then we forward these packets to possibly multiple ports. We can define that in the user interface, and although we can only create 7 different packets initially, we then apply an individual modification of each packet on each port. So we can have different Ethernet addresses on the different ports, different IP addresses, and so on. So actually, we have more than 7 different packets. We can have more than 7 different flows. The P4TG header contains a 32-bit sequence number for packet loss and out-of-order detection, as well as a 48-bit timestamp that we use for the RTT calculation. So we tag the packet when we send it out, and when we receive the packet back, we can calculate the round trip time. And we also have an 8-bit stream identification field to identify the different streams that we have defined within P4TG. The packet forwarding in P4TG is a bit unusual or a bit different than you could expect. I already said that we can have 10 ports that can generate up to 100 gigabit per second, so in total 1 terabit per second, and that's the reason why. We have 10 front panel ports on the Tofino that we use for traffic generation and reception, and then we have per traffic generation port additionally 2 recirculation ports, so ports that are in loopback mode. When we send a packet to that port, it is directly recirculated and we can reprocess it again. We call these ports PR out for the send side of the traffic generation and PR in for the receive side. And what we do is that when we receive a packet on a port, let's call it P in, we receive that packet and then we forward it to its corresponding recirculation port PR in. There it is recirculated, and then we are done on the receive side. When we generate a packet and send it out, it is first generated on an internal traffic generation port in the Tofino. And instead of directly sending it to its appropriate port, we first recirculate it via the PR out recirculation port and then send it to its final destination. And we do that so that we can collect statistics during the recirculation so that we have basically 2 pipeline runs to collect all statistics that we need. Our prototype is a 32-port Inter-Tofino with 2 pipes. And now we can do the math. When we have 10 ports, front panel ports for traffic generation and reception, each port has 2 additional recirculation ports, then we only have 2 ports left on the device, and that's why we can't have 11 ports or more. When you have a larger Inter-Tofino with 64 ports, for example, you can use more than 10 ports for traffic generation and can also have more than 1 terabit per second total generation capacity. Okay, now we know how the traffic generation works and what the packet path is roughly within the pipeline. Now let's have a look at the statistic collection that we do, which is only done in the data plane. I already said we have like layer 1 rates, packet loss, and so on. And internally, all these statistics are stored in registers. We use a composed 64-bit register, which is composed of multiple 32-bit registers to store the total amount of sent and received bytes per port. We use 64-bit registers so that we don't have to deal with overflow. With a 64-bit register and byte counter, these registers will never overflow. Later, we will correlate these values with the hardware timestamp of the Tofino, which has a nanosecond precision, and then can use these values to calculate a very precise rate within the control plane. As an example, when we would use TCP dump timestamps without hardware acceleration, then we have an accuracy of roughly 100 microseconds. So these Inter-Tofino timestamps, they are very precise. We also use 64-bit registers to store the number of lost and out-of-order packets. And then we have additional registers for the inter-arrival times, a 32-bit register to store the running sum of the times between consecutive packets. So the sum and the number of packets within this metric, the same do we do for the absolute error, so the deviation of the inter-arrival time to its mean. And with this approach, we can calculate statistics over the inter-arrival times over all packets and don't have to do packet sampling, like in the case for the round-trip times. And finally, we also collect statistics that are not stored in registers. Therefore, we use table counters, so to counter externs, for example, for the frame types or the frame size. The good thing with the register values is that they are hard real-time, so we get always the latest results. With the table counters, we have a bit of an offset because we need to synchronize the data plane to the control plane, but nevertheless, these counters are still very accurate on a time basis. And in the last step, we need to retrieve our statistics that we collected in the data plane, and this is again split between the control and the data plane. And for that purpose, we regularly send the register-based statistics to the control plane, and we do that with the help of monitoring packets. The internal traffic generator does not only generate the traffic that is forwarded, it also generates repeatedly monitoring packets. And a monitoring packet follows then basically the generated path of the packets that are forwarded. So we recirculate always between these PR out and PR in recirculation ports. And at each recirculation, we collect all statistics. We get a transmission timestamp in the monitoring packet, as well as all these counters from the registers, like the layer 1 byte counter, the layer 2 byte counter, the packet loss, the stream-based counter out of order packets, and the port number where these statistics have been collected. And then we create a digest, send it to the control plane, and the control plane knows exactly at the time of the timestamp, the counters for the given port were as follows. The counter-based statistics are also regularly read by the control plane through the normal gRPC interface. So we have a synchronization operation, and then we can simply read these counters and visualize them. Next, I want to show a bit how accurate is P4TG and what rates can we achieve. To that end, I want to show the following plot where we generated constant bitrate traffic with minimal sized Ethernet frames with 64 bytes. This is generally rather difficult because we need to generate many packets because it's the minimal sized Ethernet frame. We configured different target rates from 10 gigabit per second to 100 gigabit per second, and then measured what P4TG actually generates. And what we can see here is that we have quite a high generation accuracy. It's typically in the order of 99%, but we have sometimes small deviations. And this small deviation is actually wanted because we want to have a trade-off between the burst size that we generate, so the number of packets that are sent back to back, and how accurate our rate is. Too large bursts may be difficult for other networking equipment. That's why we want to limit the burst size. We have in the controller an integer linear program that actually optimizes an objective function that finds a trade-off between the burst size and how accurate the resulting rate will be. We also have a precision mode where we strictly limit the burst size to 1, so only a single packet at a time. But with this approach, we might not meet every rate as accurate as possible, and therefore we have the rate precision mode where this automatic trade-off is done. We can not only generate constant bitrate traffic, but also Poisson traffic, which is a bursty traffic and typically known to have exponentially distributed interarrival times, which are typically called random. Of course, we can't do an exponential distribution. Therefore, we use the discrete approximation through the geometric distribution. And what we see here in these plots is a measurement over the seen interarrival times when we generate Poisson traffic. The yellow line are the measured interarrival times. The red line is the theoretic optimal exponential function in the Poisson process. And the blue line is the discrete geometric distribution in theory. And what we see here is that the measured values nicely fit between the geometric and the exponential function, both with 50 gigabit per second as well as 75 gigabit per second. So P4TG also accurately generates Poisson traffic, which is sometimes needed for some kind of scientific experiments where we want to have some kind of bursty traffic. Last, I want to talk a bit about some use cases where we have applied P4TG and where others have applied P4TG so that you can get an idea what you can do with P4TG. As a first use case, we evaluated the performance of the Aruba CX10K, which is a switch that is actually composed of two different switching ASICs. It has two AMD Pensando P4 DSM ASICs, which are P4 programmable, but not for the public. And they claim that they have 100 gig L4 stateful firewalling within these chips. And then they also have a Broadcom Trident 3, which does the regular switching and routing within the device. And we wanted to test, do we really get 100 gig layer 4 stateful firewall, or in our case, stateless firewalling? And to that end, we also wanted to see whether the number of firewall rules has an impact on the performance. And we measured both the layer throughput in gigabit per second as well as the MPPS. And what we can see here is that we don't get always 100 gig layer 4 stateful firewalling. When we have two small packets, we get a performance cap at around 20 gigabit per second on layer 2. And we need roughly a packet size of 1024 to get up to 100 gigabit per second on layer 1. But interestingly, the number of firewall rules doesn't matter. And the reason for this throughput cap is actually the MPPS cap of the AMD Pensando chip, which seems to be around 36 MPPS. So we have to go higher in the packet size to get the 100 gigabit per second. Another use case was an evaluation of another P4-based implementation that we recently did of a mechanism which is called per-stream filtering and policing, PSFP, which is a mechanism in time-sensitive networking. PSFP has a so-called gate scheduling mechanism where we can define time periods where traffic should be forwarded and time periods where traffic should be dropped. So in this case, a gate is either open, traffic is forwarded, or a gate is closed, traffic is dropped. And these gate changes, they repeat in a periodic manner, but the change can be really fast in the order of microseconds. And we needed a way to evaluate the forwarding behavior at line rate with 100 gigabits per second. And to that end, we had one Intel Tofino with our P4 PSFP implementation, another Intel Tofino running P4TG. We generated VLAN traffic with 100 gigabit per second, and then applied our PSFP implementation and monitored the receiving traffic. And what we saw is exactly what we expected. When a gate is open, traffic is forwarded, and when a gate is closed, traffic is not forwarded. And when we look at the x-axis, the time scale here is really low, in the order of microseconds. And with P4TG, we were able to generate the amount of traffic and measure it to get our results and to validate our implementation. And a last use case is from a company, ByteDance. ByteDance currently uses P4TG for a proof of concept for their performance testing of cloud gateways, for example, with the VXLAN capabilities. And they use P4TG because the costs for software-based traffic generators does not scale that well when you go to higher throughput requirements like 1.6 or even 3.2 terabits per second. Then you need many servers with many NICs, and that's quite costly to generate this amount of traffic. And in comparison, an Intel Tofino is cheaper and gives you up to 1 terabit per second out of the box. So this is some kind of cost optimization here. Other companies are already testing P4TG as well. Okay, last but not least, I want to give a small demo here in quotation marks because it's not a live demo. Never do a live demo. It's rather a series of screenshots, but I hope that the workflow is still obvious with this one. So we start P4TG and first configure the streams that we want to generate. And we can define up to 7 different streams here with a given frame size and a target rate. For example, we want 64 byte frames with 10 gigabit per second. We want precise inter-arrival times, so the burst size is always 1. We don't want a VXLAN tunnel and no additional encapsulation. And then another stream with 1024 bytes, 1 gig, and so on. Then we can configure which stream should be forwarded over which port. For example, here we configure that on port 1, stream 1 should be sent, and we expect the returning traffic to be received on port 2. Of course, we could also say that stream 2 should also be sent on port 1, and that stream 1 should be sent on multiple ports simultaneously. That's possible, and we don't have to use the first 10 front panel ports. We can configure that as well. And in the next step, we can configure the stream individually per port. So we can say on port 1, the Ethernet addresses should be different than on port 3. We want IP address randomization on a specific port. We want a specific MPLS stack on one port and another stack on another port, so we can individualize each stream. So although we can only define 7 packet types and rates in total, we still get more than 7 different flows and different packets. When we start the traffic generation, we get a nice visualization about traffic rates, packet loss, and RTT over time, as well as the total send and receive rates on layer 1 and layer 2. We also get the send and receive inter-arrival times, both the mean as well as the mean absolute error. In this case, it's a Tofino to Tofino connection, so there's no traffic distortion. That's why these values are the same. We don't have packet loss because Tofino to Tofino connection, no need to drop packets. And we have, of course, very low round trip times in the order of 1 microsecond and only a very small jitter. We also get statistics about the frame types on the send path and receive path, how many unicast packets, how many VLAN packets, how many IPv4 packets. Down below the page, there's also the statistics for the frame sizes and so on. We can also get these informations on a per port basis, so not only the summary, we see it here in the tab, as well as some statistics are also measured per stream, which you can also inspect. This brings me to the conclusion of my talk. P4TG offers traffic generation at very high data rates with up to 100 gigabit per second per port. And there is even the possibility to go up to 400 gigabit per second with the Intel Tofino 2. We in Tübingen don't have an Intel Tofino 2 yet. We only have an Intel Tofino 1. That's why P4TG is not yet tested and ported to the Intel Tofino 2. We plan to do that. The Tofino 2 is already ordered, so we will update later. In general, it's a very low-cost hardware-based traffic generator compared to commercial solutions, and at least for our use cases, the functionality is sufficient. It is customizable for individual needs. Both the data plane and the control plane is open source on GitHub. You're free to adapt it to your needs. We also published a paper about it in IEEE Access, and of course, we are open for contribution. So if there is a missing feature or protocol that you would need for an evaluation, you're more than welcome to open an issue or a pull request. We're happy to work together with others so that we can get features into P4TG that are useful for others. Thank you very much for your attention, and I'm happy to answer any questions that might come up.
Thanks, Steffen. I think just to warn you, they're nice folks, but some of your competition is here listening and probably has more detailed questions than I do. But I think we'll open up for questions, and please go ahead.
Hey, Steffen, it's Glenn Gibb here. Nice presentation, and looks like a very exciting product. I guess I've got a bunch of different questions. First of all, if you had the 64-port variant instead of the 32-port, do you expect to be able to do 2 terabits without problem? Or is there some scaling issue going up to 2 terabits?
No, it depends. It depends on the packet size.
Sure.
So with large packets, of course, but as we basically use all ports because we do these expensive recirculation, when we use traffic generation on 20 ports, we actually use 60 ports because we recirculate it always.
Yeah.
So we have more MPPS than you would expect. So not the 2 terabit MPPS, but actually the 6 terabit MPPS. And when there's a limit on the MPPS that we might hit, then of course there we are limited. But for larger packet sizes, I would definitely expect to go to 2 terabit per second.
Sure. And then
if you remember, second question, you said the recirculation was because you needed more processing for with the extra pass for the statistics.
The original reason was that we wanted the packet size, which is only available in the egress when we don't want to rely on IP header length, for example. And then we wanted to have the monitoring packet follow the same path without being sent out or without an explicit drop that we need. And that's why we came up with the initial recirculation. But when we added more and more features, it was a good thing to have because then we were able to split certain calculations for certain recirculation ports or not. So it was actually a win because we could do more processing.
Yeah, sorry, Glenn, go ahead.
No, that's okay. I was going to say, you don't support, at least presumably you don't support doing like TCP style of sort of connection emulation just because of the limitations of Tofino. I'm just wondering, have you looked at combining this or even porting this to one of the SmartNIC platforms, whether it's Intel's or somebody else's, and whether you could go to effectively emulating TCP streams or other types of streams with something like a SmartNIC?
Not yet. A few years ago, we worked with FPGAs and we're not that happy with that. That's why we stick to Tofino and P4. And of course, there are the limitations, but that would be a nice thing to also get some stateful features in P4TG. Yeah.
Well, unless somebody jumps in, I'd say keep going, Glenn. Let them fend for themselves.
That was certainly the main questions I had. Well, since nobody else is asking a question, maybe I will ask one more. What Tofino limitations did you run into while? Effectively, like what limitations did you hit in the hardware that you would, if you were to manufacture the hardware yourself, would you like to have addressed?
Well, it's always difficult to talk about Tofino limitations, right?
True.
But in general, the register size. I mean, it's known, that's public knowledge that we have 32-bit registers. So we had to use multiple 32-bit registers to emulate a 64-bit register. And of course, that's costly. And I believe in Tofino 2, we have larger registers out of the box. So
that's right.
that would be a great thing so that we don't have to deal with overflowing, for example.
Yeah.
So that would really be a nice feature. Don't have to deal with overflowing because that makes the lives easy. And of course, another thing, not specifically for P4TG, but possibility to program or to influence the queuing more effectively so that you could implement additional scheduling decisions, for example, so that you could emulate different traffic patterns or more difficult traffic patterns.
By the way, for the effectively like the rate limiting and the traffic patterns, are you relying purely on the traffic generator for that, or are you taking advantage of? I think there's at least policing built into the traffic manager.
Yeah, we don't use policing. We do a bit of a trick here to get the per-sort traffic. So we actually generate traffic at 100 gigabit per second. And as per-sort traffic is a geometric distribution, we can get this geometric distribution by dropping packets randomly with a given probability. So we generate a random number, which is then mapped to a decision whether it's a drop or not. So we get the probability. And that's an interesting way to simulate a traffic pattern, a random traffic pattern, by actually having a constant bitrate traffic pattern at the beginning. So that's a small trick that we do. But besides that, we just use the traffic generator and do not do any additional policing.
I'm glad you asked. I was wondering if you were using a trick like that.
Yeah.
And I imagine that could extend to other traffic arrival patterns than Poisson and
of course, you could simulate any traffic pattern reasonably with enough table state and a random number. So
yep. I will prompt Chris Summers here from Keysight to see if he has any comments, questions, any sales pitch for Keysight products based on. I know you said you've programmed Tofinos before, I think for Keysight products.
Oh, thanks, Andy, for not putting me on the spot.
You don't have to say anything, of course, but
no. First of all, I want to say, Stefan, this is very impressive, and it's a good use of the Tofino and P4. We're in the traffic generator business as well, and we have commercial. I'll just say we do have a commercial Tofino powered traffic generator that you might want to look up just to look at the spec sheets and compare. I won't get into it.
I'm aware of that, actually.
Yeah. So, I mean, maybe I'll say that as a way of validating what you've done here. And there's all kinds of techniques available, which we've explored ourselves. Since we're a commercial company, I'm not going to talk about what we've done or invented, but I will say this is very impressive. And, pertinent to, I think it was Glenn's question about what kind of hardware limitations there are, or someone asked that. What would you do differently in the hardware? There certainly are quirks and limits in the Tofino, which makes some things challenging to do, such as the ability of the packet generator to keep up with 64-byte packets on all ports simultaneously, etc. You probably run into some of those things yourselves, but there's some really cool techniques here that you've shown us, and I want to give you a big pat on the back for this work.
Thank you. But actually, I have to say that these limitations are, at least from a research perspective, of course, from a commercial perspective, it's different, but from research perspective, that's the fun part. So you have to get creative. Maybe it's not an optimal solution then, but it's a cool solution because you have a limitation that you have to solve.
Oh, yeah, that's what makes engineering fun.
Yeah.
If it was all easy, it wouldn't be exciting.
Anybody would do it.
Anyone would do it. Any layperson would just walk off the street and do it. No, this is good stuff, and it's nice to present this and have an open source.
Apologies too if you put up information right at the beginning that I missed. But how many people were working on the team to build this?
The implementation is all done by myself, actually.
Okay, wow, that's certainly impressive.
But
So,
it got some refactoring. So for example, the UI was not pretty in the first version and stuff like that. And the encapsulations have been step by step. So actually, I think 3 weeks ago, we added VXLAN. So that's quite new. And the paper was already published, I think, 1.5 years ago. So was not done in a week, but still done by one person.
Any other questions for the speaker on this?
oh, actually, I will ask one more question since I talked about, porting to SmartNICs or other things. How difficult do you think it would be to port to any other target? I mean, right now you're obviously relying on things like Tofino's traffic generator, but
well, I would say if there is a traffic generation capability, then the other stuff like registers, tables, that's regular P4, I would say. So it's only really the traffic generation capability. And if that's given, then I would say a port is quite easy.
okay. And the traffic generator in Tofino, I mean, I don't remember all the details of it, but it's at least at a high level, I would describe it as a relatively simple state machine, but it's reasonably precise in terms of being able to, like traffic generation rates and things like that. If you had something more like a CPU-based traffic generator rather than a hardware state machine-based traffic generator, what interesting things could you do, and what would you also lose out by having a CPU-based traffic generator?
Well, I think when we have a normal pipeline that is capable of 100 gig without packet loss, and we have a multicasting feature, for example, then I mean we can replicate a single packet to 100 gig if we get enough recirculations. So I don't think that the initial traffic generator has to be as precise as possible. At least when there is some kind of traffic generation, we could replicate packets as long as we need to get our target rate. So in theory, and then we could still apply some shaping, for example, to get a smoother rate. So I could imagine that also with CPU-based traffic generation, as long as we have a pipeline that has no packet loss at line range, we can get quite far.
Sure. Yeah, and I guess part of the reason for asking that is I'm just thinking about some of the SmartNIC implementations out there with, built-in ARM or other CPU cores and using those as traffic generators.
Yeah, I think that's reasonable to do. Yeah.
All right. Well, thank you, Steffen, for volunteering to give this talk. Really glad to have
Thanks
you
for
here.
having me.
Interesting stuff. Much appreciated.